So today is the last day of this very nice conference. And today we have Andrew Lucas from University of Colorado. He will tell us about hydrodynamics with kinematic constraints.
Yeah, so thank you for the invitation. Sorry I could only come for this last day, but yeah, today I will talk about sort of hydrodynamics with kinematic constraints, aka fracton hydrodynamics. There we go. Okay. Yeah, so this is work that I've been doing for about 2.5 years now, first with Rahul Nankishore and Andrei Gromov, and more recently a lot with Paolo Glorioso and my students Jing Kong and Xiaoyang, who are both here. And then Joaquin, who's moving to Texas A&M, helped us a lot with numerics that I'll show at the end. Okay, so just sort of a brief outline. So I'll say a few introductory comments, just introducing what hydrodynamics is and what I mean by kinematic constraints. And then I'll discuss 3 increasingly complicated examples of fluids of this type, and then run out of time and conclude. Okay, so a few introductory remarks. So, I go around giving talks about hydrodynamics, and I would say that audiences are not in universal agreement as to what this term means, which is a little bit annoying, but okay. It's an old subject with an old history. So when I say hydrodynamics today, what I mean is that it's the effective field theory that describes thermalizing many body systems. So you take the air molecules in this room, for example, and they're hydrodynamic not because they obey the Navier-Stokes equations, but because they form a chaotic many body system that tends to reach thermal equilibrium. So we have a large number of degrees of freedom characterized by some mean free path denoted as little l. And if we look on very large scales compared to this mean free path, we expect that even in a sort of local patch of the room, we can talk about a local temperature and chemical potential and so on. Okay. So the degrees of freedom in this hydrodynamic EFT will, for the gas in this room, be associated with the conserved quantities. So let's say we have mass and momentum conservation. I'll ignore energy for this talk just out of expedience. So for mass, we assign it a density rho, and for momentum, a density pi, or rho times b. And we write down a continuity equation for each of these degrees of freedom. So for charge, in this theory, looks quite simple. For momentum, a little more complicated. In each case, this equation takes the form of the time derivative of the conserved quantity plus the divergence of a current equals 0. Okay. And what hydrodynamics goes like, at least in sort of the canonical Landau framing of the problem, is that you take the currents for charge and for momentum, and you write them down as sort of the most general possible expansions that you can think of, consistent with symmetries and thermodynamics. Okay. But for the most part, maybe in a revisionist telling of history, you write down everything that you can. Okay. The expansion parameter that one uses to control hydrodynamics is an expansion in spatial derivatives. And this can be understood by thinking that, for hydrodynamics to be valid, we need the box to be very large compared to this mean free path. And the ratio of those 2 length scales is a small parameter that governs the accuracy of our hydrodynamic expansion. Okay.
So in hydrodynamics, how do you determine how much to truncate?
Oh, so the question, there's a question on the truncation of this expansion. And this is an asymptotic expansion, like pretty much every field theory. And I would say that in practice, one usually truncates it at first order, or whatever leading order causes dissipation. I mean, if you're modeling airplanes, et cetera, atmospheric fluid dynamics, this is what you would do. Maybe a little more formally, I think it depends, of course, on the precise energy scale of the process that you're looking at, the order that you would go to for an optimal result. Okay, so this talk will be about what happens when the microscopic dynamics is subject to a non-trivial constraint, such as dipole conservation in addition to charge or mass conservation. So in this example, I have something even simpler in mind than air molecules in this room. I imagine I just have a one-dimensional lattice, and the sites can either be empty or they can have a positive or negative charge on each site. Now, if I just had charge conservation, then you could think that each charge undergoes maybe some random walk, and then when there are charges nearby, maybe the random walk slows down or speeds up. But now I say, in addition to charge conservation, I want to impose dipole conservation as well. And this makes an individual charge in this theory immobile, because if it moves, it changes the dipole moment. And so the only thing that can happen is this charge has to find a sort of nearby minus charge, and then they can move together. Or maybe a little more exotically, if I had 4 empty sites, I could sort of put a plus, minus, minus, plus, something that I could create charges out of nothing so long as they have 0 net charge, 0 net dipole. So the question is, how would a theory like this thermalize with this kind of microscopic constraint on the dynamics? So we dubbed these theories fracton fluids in 2020. This was a bit of branding, which I think was successful. But the origin of the word fracton for us is just that the individual excitations are immobile. Okay, so you have to look at these sort of composite objects to see any thermalization. Okay, so the first thing I want to do is to discuss the hydrodynamics of the theory that I just described. So charges moving on a lattice subject to charge and dipole conservation. This is sort of the simplest example of a fracton fluid. First, let's just quickly review that if we only had charge conservation in this theory, what would we see? Well, the only degree of freedom would be the charge density rho, and we would see a diffusion equation for this conserved density. Now, if we add dipole conservation to this system, as I'll show in a few minutes, you find that this second order diffusion equation becomes replaced with a fourth order subdiffusion equation. Okay. And shortly after we sort of discussed this theory, there were a number of papers that presented numerical simulations that confirm this prediction. So what this plot is showing is a 2-point function of the density in the theory, and the power law of the decay with time of this correlation function just reads out the critical exponent, the dynamical critical exponent relating space and time, which is indeed 4, consistent with our prediction. Okay, so where is this result coming from? Well, so let's start with our sort of a macroscopic equation encoding dipole conservation. So maybe we'll take for granted for this page that all we have as a slow degree of freedom is the charge density rho. I'll come back to that point shortly. If that's our slow degree of freedom, then the dipole charge is the position x multiplied by rho integrated over space. And if we want this to be conserved, then not every continuity equation that we can write down is appropriate. So for example, if I take the derivative on rho, then I can replace dt rho with minus dxj in one dimension, where j is the usual charge current. And then I integrate by parts, and I find that the integral over space of the charge current has to vanish. And that is sort of certainly true if the charge current itself is a total derivative. And so we're going to write down our continuity equation for charge in this form. It's actually better for this theory to think of the fundamental current as a 2-index object, JXX, and the continuity equation for charge is dt rho plus dx squared, JXX equals 0. Okay. Now, in the spirit of Landau's formalism, we can now try to write down the most general JXX that's compatible with symmetries and conservation laws. And assuming we have spatial inversion symmetry or parity, we might first write down a constant multiplying rho plus b dx squared rho, and so on. Now, when we first started doing this, we said, well, we might as well also impose time reversal symmetry. When we have time reversal symmetry, the current J is time reversal odd, while the charge is time reversal even. And this red term, A times rho, has no derivatives. So it's effectively a thermodynamic coefficient. And if this term were present, it would mean that the parameter A is odd under time reversal, and this can't exist. So therefore, we can set A equals 0. In, I don't know, 15 minutes or so, I'll come back to the question of whether A can exist ever. But okay, if we assume time reversal symmetry, we get rid of this A term, and then we're left with this 4th order subdiffusion equation that I described earlier. Okay. All right. Now, you might ask, was it acceptable? Yeah.
Sorry, is there some kind of presumption of locality in writing down this sort of picture? Because on the lattice, I would sort of imagine that there's like whether or not the question of whether a single charge can pop depends on whether there's another opposite charge elsewhere on the lattice that pops simultaneously.
Yes. So.
So can you repeat the question?
Oh, right. So the question is about locality that, as I understand it, it's like if you have a very low density of charges, then basically every charge can't move because maybe it can only interact with charges within, you know, some number of lattice sites away. Indeed, this is a serious issue, and there's a nice paper that points out that at very low density, these theories don't thermalize for this reason in one dimension. They basically just freeze up. And so we're interested in the regime where they can thermalize. And so in some sense, an assumption going into this is that that process doesn't happen. You could imagine one way of getting around this is just that even if it's 50 lattice sites, you just say that I can interact up to 50 lattice sites away. If the lattice has 50 times 10 to the 10, this is a hydrodynamic. I can expect a hydrodynamic description, you know, on maybe 1,000 lattice sites and beyond. Okay. Right. So now I want to turn to this question of is it sort of fair in these constrained fluids to say that the only hydrodynamic degrees of freedom are associated with charge density? So you might think, for example, well, I could have some density of bound states, like dipole bound states that diffuse around sort of independently of everything else. And I claim that those will not exist. So you don't need to worry about any extra degrees of freedom. And the process that ruins any sort of conservation law for bound dipole states is the following. So here, these gray boxes you can think of as sort of coarse-grained sort of blobs that, you know, in my hydrodynamic theory, I've coarse-grained out the lattice scale, and I'm counting the charge in each of the blobs. That's my charge density. Okay. Now, in the sort of blob on the right, I see I have a bound dipole state, minus plus. And note that charge and dipole conservation allow me to take this configuration where the left blob has net charge, the right blob doesn't, but has a dipole. And I can convert this into a state where there's no bound dipole state in either blob. I just have moved the sort of plus charge from the left to the right. Okay. So unless you sort of artificially impose that the bound states themselves form a conservation, form a conserved charge that, you know, commutes with the Hamiltonian or the quantum circuit, et cetera, then you will not get a degree of freedom associated with bound dipole states. Okay. And this is analogous to why, if you write down the conventional Navier-Stokes equation, there's no angular momentum density, even if angular momentum is conserved. In fact, you can sort of, in retrospect, think of angular momentum as a sort of dipole charge for the conventional fluid. Okay. So that was all about the sort of the general theory of dipole conserving fluids. But let me show you a sort of a nice microscopic realization of this. So this is an experiment that was actually done in 2019 before we started thinking about this theory carefully. So the experiment consists of fermionic atoms trapped in an optical lattice. And with AMO magic, they have engineered the Fermi-Hubbard model in their optical lattice. Okay. And so then a grad student sort of picks up the apparatus and just holds it at an angle. That's a joke, if it's not clear. But they tilt the optical lattice, and what this does is it causes, a gravitational potential due to this experiment taking place on Earth. And what happens if you simulate the Fermi-Hubbard model in this gravitational potential? So imagine you put this in a pretty generic excited state. It has a lot of energy. It will thermalize. This is a strongly interacting system. And what we would expect is that, okay, on very short length scales where this gravitational tilt is negligible, you'll get some diffusion modes for charge and energy. And they're coupled in general, but you just have two diffusion modes. However, when you start looking at very long length scales, you notice that this sort of gravitational potential energy is super extensive. It grows with the system size. And so no matter how small f is, if the system is big enough, this gravitational potential wins at the end. And basically all the energy is captured entirely in this gravitational potential energy. And what this means is that energy is basically dipole in this theory up to subleading corrections. So actually we expect that in this theory, you should have the hydrodynamics of charge and dipole conservation, which predicts a single subdiffusive mode. And indeed, if you ask what happens both on short and long scales, you can see on short scales that you have diffusion of charge and kinetic energy, if you like. And these modes sort of collide as hydrodynamic poles in the complex plane, and one of them becomes subdiffusive, and the other one just picks up a finite lifetime. Okay. So indeed, this theory is in our universality class, even though microscopically there's no dipole conservation. And this experiment was done in 2019. And when there's no tilt, you can, what they do is they, I don't know, have a few hundred sites. They prepare dipole, they prepare charge density waves of various wavelengths in the optical lattice, and they ask how long it takes for the density wave to relax. And from this, they can extract basically the time to relax this wave should scale with wavelength squared if you have diffusion, and wavelength to the fourth if you have subdiffusion. And they can indeed see that as they crank up the tilt, there's this nice transition between 2 and 4. Okay. Yeah.
Elaborate on why energy, why the energy fluctuation slightly becomes gas.
Sure. So roughly what happens is that if you look at, let me make sure I say this correctly. Okay, I might get this backwards, but roughly what happens is that when you add this forcing term, so you can basically take your charge and energy equations and you add a kind of source term due to the gradient of the potential. You can think of this as sort of a chemical potential for the density. And what this does is it takes, I think, the chart, you get a term in the energy continuity equation, which on the right-hand side looks like F times the charge current. And if you think through carefully what that implies, it's going to imply that the charge current becomes approximately the gradient of the energy current. And since there's a term proportional to E in the charge current, again from the forcing, you find that energy can relax. So that's where this F squared comes from in this relaxation time.
It's a simple way of saying that, perhaps, that there's effectively a dual heating term that arises in energy conservation.
Sure, yeah. You can think there's a Joule heating term if you want. Yeah, that's basically the same physics. Okay. Okay. So now let me move on to a sort of slightly more sophisticated version of this story, where now we want to take our dipole conserving theory and ask what happens if we start breaking space-time symmetries, in particular time reversal symmetry. Remember that part of the argument that we gave for having quartic subdiffusion was that if we tried to write down this constant term in JXX with no spatial derivatives, that would mean that this parameter A had to be T odd, and so we could set it to 0. But now suppose that we don't have time reversal symmetry. Now, why not add an A term? That could be finite. As it turns out, you're not allowed to write down this term even when time reversal is broken and spatial inversion is broken. And the sort of punchy explanation as to why it's not possible is this violates a fluctuation dissipation theorem. Now, you might say, where is this coming from? How can we say that? For example, the numerical simulations that first looked at dipole conserving dynamics, at least not in this sort of emergent setting of the Fermi-Hubbard model, the first papers that were doing this were looking at classical Markov chains. So you just have a bunch of charges on a line, and the update rules happen to conserve dipole moment as well as charge. We can certainly devise that Markov chain to have no time reversal symmetry, but there's no energy conservation. So what are we talking about when we say there's a fluctuation dissipation theorem? So the upshot is that we have there's an old literature on stochastic processes and random dynamics, and we've tried to and are in the process of sort of rewriting and reinterpreting some ideas that have been scattered around in the literature, and sort of thinking of them in the kinds of EFT methods that this audience will be more happy with. And it turns out that when you do this, even in non-thermal systems, there's still strong senses of time reversal and fluctuation dissipation theorems, etc. So for the next part of the talk, I'll sort of sketch out how this works and how we can apply it to rule out this A times rho term. So it turns out even with time reversal symmetry, you still have this subdiffusive dynamics. So the key observation for building these EFTs without time reversal symmetry is that even when you just have a Markov chain, there's no energy conservation, there's no temperature, you still have a stationary distribution for the stochastic dynamics. Okay. And let's write that distribution as e to the minus phi. Now, okay, I wouldn't have made this remark if it wasn't necessary for later. It turns out that there's a particular function mu, which is basically the derivative of phi with respect to rho. This kind of chemical potential will show up everywhere in our formalism, okay? And okay, so here it is. It's sort of our emergent thermodynamics. And okay. The strategy that we're going to have is sort of pedestrian. So in the 1970s, there were path integrals that were devised for stochastic processes by Martin, Sigia, and Rose, or MSR. And in a nutshell, the MSR actions will correspond to, for every field, so for us, this will just be one rho, there will be a sort of conjugate noise field, which I'm calling pi here. And what MSR did is they essentially took the stochastic equations of motion. You use the delta equals e to the I lambda, et cetera, identity to write that equation of motion as a path integral. You integrate over noise, and this pi kind of becomes the dual field to rho. Now, ordinarily, one starts with the SDE and builds the MSR functional from that, but we would like to invert the process and build the MSR functional directly and constrain H, kind of using EFT principles. Okay. We're talking about hydrodynamics with multiple conservation. There will be 3 symmetries, or at least transformations, that will be important for us. The first one is to know what it means for this MSR action to encode charge conservation or multipole conservation more generally. And it turns out that with a few lines of algebra, you have a conservation of rho multiplied by some function f of x whenever the action is invariant under shifts of pi by an arbitrary function of time multiplied by f of x. Okay. So for charge conservation, this just means pi is invariant under spatially homogeneous shifts in x. Parity and inversion are kind of trivial for us. The charge is parity even, as is pi. What's less trivial is time reversal symmetry. So time reversal symmetry will flip the argument of time as before, but it will also do something a little more interesting to our sort of noise field pi, and it will shift pi to minus pi minus I mu. So this is why I had to define this stupid mu function earlier, because it shows up right here. Now, there are sort of 2 arguments for where this comes from. One that maybe will become appreciated in a few minutes is that if we didn't have a transformation like this, there would be no interesting dynamics. So we couldn't just say pi flip sine. It has to do something more non-trivial. And then you can ask, well, how much more interesting can the transformation on pi be? And it turns out that this is basically the only thing it could be that's compatible with sort of EFT. Because if you apply time reversal twice, pi has to go back to itself. And you can classify what are the functional transformations that have this involutive property. This is the only one that is sort of compatible with a derivative expansion or a small, an expansion in small pi. Yeah.
It's real.
No, not. Well, the contour, the integration contour is conventionally taken along the real axis. And so you can think that indeed this transformation, one perhaps interpretation is shifting the integration contour of pi.
But in a way that depends, mu is the field that you're integrating over is all
Yes.
being shifted in a field dependent way.
Yes, I'll admit that we don't often think about sort of actually doing this path integral, but it has to be this, as it turns out. One way that you can see this is that, so let's say we want time reversal symmetry in our dynamics. If we want time reversal symmetry, then we want the transition matrix. So here I have in mind a whole many body configuration at time 0, a whole many body density configuration at time t. What's the probability that I go from one to the other? That should be equal to the probability of going the other way up to a phase factor that depends on the relative difference in phi evaluated on those 2 configurations. Mathematically, this is what it means to have time reversal symmetry in a random system. If you want this condition to be obeyed, then roughly speaking, you need this transformation to correspond to time reversal. Okay, John McGreevy raised, so you can ask a question.
Yeah, thanks, Andy. Sorry, could you explain why with this particular imaginary shift of pi, this transformation squares to 1? I didn't understand.
Oh, so, okay. On the blackboard, this would have been a little easier, but basically, okay, suppose you take this pi in this equation and think of it as, oh, is it visible? But let's see.
I think if you tilt the screen down a little bit.
Wait, is that visible for you? Or? Oh, wait. Okay, oh, I see. I'll just move the screen. Okay. Okay, so if you take pi to minus pi minus I mu, and then this becomes minus clear.
Oh, so it would have been true for any imaginary shift, or sorry.
Yes. So the argument I gave doesn't fix that this function has to be mu. Fixing that it has to be mu needs the second argument, basically, about detailed balance.
Okay, thanks.
Yeah. Okay. Now, as a sort of annoying technical aside, it turns out that at the fully nonlinear level, this transformation isn't quite correct. And we have a slightly better picture for how to think about the theory, which is sort of ongoing work. But okay, I'll just mention that caveat. But in practice, for what we'll do today, it's good enough to just think of this transformation. Okay. All right. So with just this sort of vanilla EFT for stochastic dynamics, we can sort of start building increasingly complicated theories. So let's start with just vanilla charge conservation in 1D. This is really the simplest possible thing we could expect. We're just expecting to find Fick's law. Now, it turns out there's really one term you can write down at leading order. So you can take a function d that depends on rho, and you can multiply it by dx pi plus I mu. Okay. So a number of comments here. First, it has to be dx pi that shows up because of charge conservation. So pi is now invariant under shifts that are homogeneous in space. We have to have pi and pi plus I mu showing up together in this way because that is compatible with this time reversal transformation. That's the only thing we could have done. Okay. And then lastly, this function d of rho has to be positive because this is a complex action and it needs to have a positive imaginary part. Otherwise, the path integral will be sick. Okay. Now the fact that, so a little bit about the structure of these actions. The terms that are linear in pi correspond to the equations of motion. Okay, so you vary Lagrangian with respect to pi, you get the continuity equation. The dx pi term encodes noise in a way that I won't explain. From that, we can deduce that this d must be the diffusion constant of the theory. And now observe that you also get a dx squared pi term whenever you have dx pi, dx mu. And that's essentially the fluctuation dissipation theorem. But now there's no finite temperature. Essentially, this comes from the stationarity of the process. That there exists some stationary distribution that this Markov process tends to. We know what it is, and therefore we can demand that L is invariant under. Basically, that L is compatible with that stationary distribution that forces us to write down this formula. Okay. So now let's break this spatial symmetry down to only the combination of parity and time reversal. Space-time symmetry rather becomes PT. So you can still do, you just need to combine the parity transformation with the time reversal one, and you get a sort of quote unquote generalized KMS symmetry. And it turns out under this smaller symmetry, there's a new term that you can write down. Which is an arbitrary function of mu times dx pi. This is indeed invariant because if you apply our time reversal transformation, it's just a total derivative. And what this orange term corresponds to is essentially adding bias to your random walk to your diffusion equation, which is indeed consistent with a reduction of space-time symmetries down to PT. Okay. And in this formalism, any drift term is possible. This is actually a sort of technical mystery in some respects because in other EFT methods, there are only two choices of B that are possible, one corresponding to a Galilean boost and one to a chiral anomaly. But here it seems as though there's a slightly broader family, and we don't understand this point, I would say. Okay, but let's now move on to the dipole and so on conserving theories. With dipole conservation, you now have to have two derivatives on pi, not one. That's to encode dipole conservation. And you turn the crank just as before, and you find that there's only one term you can write down. Now this number C is a constant. It's not an arbitrary function. Okay. And it's sort of similar to what we would have had in the biased random walk case. Yeah. One thing that you'll notice is there is indeed no term that's a function of mu or any function of mu multiplied by dx squared pi. And a sort of heuristic way to understand that is that if you tried to write this term down, when you do the time reversal transformation, you pick up a term that's independent of pi. Okay. And this is not allowed, roughly for the following reason. Mathematically, any theory, assuming we've correctly identified its stationary dynamics, there must be a time reversed partner for any theory. And this time reversed partner will also be a stochastic process with the same conservation laws, even if it's not the same theory. If you apply time reversal to this theory and you get a pi independent term, it's sort of breaking the assumptions that it's basically saying that this T reverse theory is not a well-behaved stochastic process. And so this rules out the existence of any term other than this orange one, no matter how many spatial symmetries you break. And you can repeat this process with quadruple conservation. So now you need 3 derivatives on pi, and you can find 2 constant terms when you break time reversal. But okay, this story sort of continues to more and more complicated theories. Hopefully the pattern is sort of clear. Okay, so there's sort of 2 effects that might be interesting when we break time reversal in these theories. One of them is just that, like the biased random walk, adding these time reversal breaking terms could sort of, have some kind of dipole conserving analog of bias, where you add a lump of charge to your system, and maybe the lump becomes kind of distorted in a space-time non-inversion symmetric way with time. So that can happen if you start adding, this kind of term, for example, in the quadruple conserving theory. But more interestingly, it's also possible that these time reversal breaking terms can be relevant perturbations in a field theoretic sense. So it's been known for a long time that one can analyze these fluctuating hydrodynamic systems using the same kind of RG methods that are used in usual quantum field theory. And we can ask essentially, if this function mu of rho is nonlinear, which it generally will be, is this nonlinearity a relevant perturbation or not to a Gaussian fixed point? And it turns out, without explaining the calculation, that this is indeed the case in low dimensions. So it depends on whether this n is even or odd. This is basically because of how many derivatives you need to add in the orange terms. But okay, suffice to say that the larger the multipole moment that's conserved, sort of the more relevant these time reversal breaking perturbations will be, and the higher the upper critical dimension can become. So in principle, these fluids have instabilities in effectively all dimensions if you just add enough multipole moments that have to be conserved. So we've run sort of large-scale simulations of classical Markov chains with conserved quadrupole charge and with update rules that either preserve or break time reversal symmetry. And with time reversal symmetry preserved, we see a dynamical critical exponent of 6. This g of t is kind of a particular spatial correlation function or average thereof that just extracts the time-dependent exponent z, the dynamic critical exponent. And when you break time reversal, you find that, okay, at early times, because this time reversal breaking is weak, you see the same scaling as before, z equals 6. But eventually you see that the decay becomes faster and it becomes more like z equals 4. And we think that this is sort of decent evidence for the existence of this new dynamical universality class. All right. So now I'd like to talk about sort of the most sophisticated version of this story.
On those plots you just showed, what was numerical data and what was fixed?
The blue line is the numerical data, and the little black dashed line is the fit to the scaling law. John has another question.
Sorry, do you understand what the instability is to?
Yes, well, okay, the instability is driven by this term. I don't think we have I don't have a sort of colloquium picture for what is driving this instability, but mathematically that's where it's coming from. Okay.
But I think the question is not what is the origin of the instability, but
The endpoint of the instability is also an open. I mean, okay, we think numerically that we're seeing whatever this fixed point is, but how to characterize it is an open question. I mean, this is, yeah, I'll give another example of this fixed point in a little bit where we have analogs that we do understand maybe better. But in general, this is also sort of an interesting open question, I think. I don't think this is a theory that's previously been found in another context. Let me put it that way. Okay. So in the last part of the talk, I will now turn to the most sophisticated version of one of these kinematically constrained fluids, which has both dipole and momentum conservation. So here I'm going to be much more schematic. The equations are kind of ugly, and I got tired of writing them down on the plane. Okay. So now we want to ask the question of what happens if we have both charge and dipole and momentum all as conserved quantities. You might think, okay, this is a bit stupid, but actually there are very simple models that have these symmetries, so just bear with me. Okay, so the degrees of freedom that we expect to have are a charge density rho, a momentum density pi I. So pi will no longer mean the noise field, now it's the momentum density. And then the dipole charge, which is the integral of rho times xi. Okay. And the algebra that relates the conservation laws is called the multiple algebra. It looks like this. And in particular, note that the dipole and momentum do not commute. Okay. And here I'm using Poisson brackets because we're mostly thinking about classical simulations, but in quantum mechanics, there's an I. Okay. And this last term makes hydrodynamics subtle and interesting. All right. So schematically, the structure that we would expect in hydrodynamics is as follows. So for charge conservation, we have dt rho plus the double divergence of a current equals 0. We've already argued for that double divergence a long time ago, so it's the same argument here. Then for momentum, we have dt pi I plus the divergence of a stress tensor equals 0. Okay. However, you can't just immediately go writing down terms. The most subtle thing here that we'll need to be careful about is that the theory has to be invariant under a very unusual kind of transformation, which is that the momentum density can shift by a constant vector multiplied by the charge density. And this is a consequence of the non-commutativity of dipole and momentum. Okay. It's helpful, I mean, even just purely mechanically, when you see something like this, it's very helpful to write the degree of freedom phi equals pi divided by rho, such that now the theory is invariant under constant shifts of this phi vector. Okay. And so even if you want to just do a Landau kind of formalism, you want to write it in terms of rho and phi, not rho and pi. Okay. And then, for example, any entropy density or any thermodynamic free energy you wanted to write down is dependent only on gradients of phi. And this is sort of reminiscent of what you would expect for a Goldstone boson. Okay. But I'll come back to this point at the end of the talk, but I'd just like to sort of highlight this already. Okay. All right. Now, you can turn the crank and it's really tedious. It's kind of ugly. So let me just sort of state the answer. So you turn the crank on this theory and you find that the hydrodynamic modes consist of a sort of sound wave coupling the longitudinal momentum and the density. This sound wave has a sort of unusual dispersion relation. The real part is k squared. The imaginary part is k to the 4. and the transverse momentum is purely subdiffusive. Okay. These exponents being doubled as a consequence of dipole conservation. And again, you can sort of ask, is the Gaussian fixed point stable? And you find that it is not below 4 spatial dimensions. Now, in this setting, there is a sort of analogy that we can appeal to, not necessarily to understand microscopically how to think of this instability, but there's at least an analogy to guide our thinking. In a fluid that doesn't have dipole conservation, so just charge and momentum, obeying the Navier-Stokes equations, there's also an instability of the stochastic equations in 2, where it's marginal dimensions, and in 1 dimension. In 2 dimensions doesn't really matter because we use the Navier-Stokes equations to describe atmospheric fluids, which are 2-dimensional. So in 1 dimension, the instability is a bit more important. And on a laptop, you can simulate that a fluid will be described by the KPZ fixed point, not by Navier-Stokes equations. Okay. So this is some very famous dynamical universality class discovered in the 80s in the context of growing surfaces, but it's also well known to be the endpoint of the instability of the NS equations. Okay, Navier-Stokes. So in some sense, we can say that what we're finding is a sort of fraxonic generalization of this KPZ universality class that's protected by dipole conservation. And okay, this is again maybe more of a branding exercise than physics, but that at least tells us what this theory will flow to at the endpoint of its instability. It's not the KPZ universality class, right? It will be different, but it's at least sort of got that same flavor. All right. So now that we've sort of claimed that there will be this instability of hydrodynamics, we can ask whether we can verify this prediction. And to do that, we would want a model that we can actually simulate with these conservation laws. And actually, there is a very nice model that has dipole and momentum conservation. And it's just this classical Hamiltonian system, which basically looks like a bunch of particles interacting in a line with some anharmonic potential. This is really a minimal model for simulating hydrodynamics in 1 dimension, except that ordinarily the kinetic energy would be p squared over 2. Now it's sort of delta p squared over 2. That delta p ensures that we have dipole conservation. It's really just analogous to momentum conservation is invariance of h under constant shifts, uniform shifts in each particle's position. Dipole conservation is that h is invariant under uniform shifts in each particle's momentum. These kinds of Hamiltonians, something like them has actually been written down before. In the quantum Hall fluid, there are papers that write down Hamiltonians like this, except usually there, this kinetic term is more non-local. Like you just would say pi minus average p. So here we want a local Hamiltonian, so we've done it this way instead. This Hamiltonian also arises at least as a sort of weird modification of the linearized Heisenberg ferromagnet. Okay. But if you linearize the Heisenberg ferromagnet Hamiltonian around a sort of point where all the spins are aligned, you find a Hamiltonian that basically looks like this, where p and x are the 2 other components of spin. So this Hamiltonian is actually not as kind of funny as it might look. And we've simulated this. We call this model A because in our paper we have another model that I don't have time to discuss today. But in model A, we basically throw it random initial conditions, and then we ask at some later time what's the typical wave number of fluctuations. And this gives us a crude estimate of our dynamical critical exponent z, since the typical wave number should, by dimensional analysis, scale as t to the minus 1 over z. Now, in this potential, it turns out that this g term is responsible for the most relevant perturbation. And so if we set g equals 0, then we expect very mild relevant perturbations. And when we do simulations, we actually can't tell that the dynamic critical exponent is not 4. It seems quite close to 4, actually. Was there a question?
You said this is only for 1 dimension.
Yes, I won't show it, but we have a higher dimensional version of this, which has a sort of similar structure, but it's in our paper if you want to look at it. You have to be careful though, because you don't want, it's roughly like this. So in one dimension, this Hamiltonian describes both a solid and a fluid. But in higher dimensions, you have to be careful whether you're getting a solid or a fluid. And okay, so the fluid extension of this is described in our paper. Yeah, anyway, okay. So without this G perturbation, you basically see something quite close to the sort of naive exponent of 4. So it's, if this fixed point is unstable, hardly so. But when you turn on this perturbation G, which turns on the most relevant perturbation to hydrodynamics, you find that this dynamic critical exponent becomes quite different. And now it looks compatible with 2.5, which is a very rough estimate of ours for the critical exponent at that fixed point. And I would say at a minimum, there are obviously error bars on these numbers, but it's certainly clear that these two exponents are different. Okay. And so we've certainly triggered some unstable flow to a new fixed point by turning on this perturbation, and that sort of, I think, is good numerical evidence for the existence of this dynamical universality class. We've also done these simulations in 2D with about 1 million degrees of freedom. And you can again, so here we're just looking at the perturbed theory, but you can see that it flows to a non-trivial fixed point, again, with a critical exponent of about 3, which is very different from 4. And yeah. Okay, so we're sort of currently working on writing up an effective field theory for this dipole and momentum conserving fluid. It's been a somewhat painful process at times, but we're working on it. And okay, it's very messy, so I'm really not going to say anything about the technical details. One thing I'll highlight is that this approach gives a sort of simple setting where this dipole conserving theory can be coupled to a metric or to Vielbein. We won't really have very much to say about this, but I think that this is a sort of appealing thing about this, this formalism, because it's been quite hard in the past to think about coupling sort of fractons and constrained matter to space-time geometry. Okay. The more interesting thing for this talk, which pops out of this formalism, is that it turns out that as you turn the crank, this ratio of momentum and charge density that I had called phi I before also shows up quite naturally, and it shows up in a very special way in this EFT. The place that it shows up is that it looks like the phase field associated with dipole symmetry. So, okay, at least in the sort of Glorioso and Liu et al. Formalism for thermal EFTs, the degrees of freedom are phase fields for conserved charges. But ordinarily, these phase fields only can show up with time derivatives in the action in a fluid phase. And ordinarily, when these degrees of freedom show up on their own, it's because a symmetry was spontaneously broken. Okay. And so this is sort of our first maybe hint that it looks like this phi is the Goldstone boson of spontaneously broken dipole symmetry in all spatial dimensions. Okay. So this is kind of the point which has held us up on writing this paper because it turns out to be a bit subtle. But let me sort of discuss the aspects in which this theory seems to have SSB and one in which it seems not to, or at least not in a usual way. So firstly, as noted before, this field phi transforms the way you would expect. Okay, so if you do a dipole transformation, you see that this phi shifts by a constant. Now, maybe a bit more mathematically, it turns out if you try to look at sort of finite size versions of this, finite size resolutions of this fixed point, the most natural way to do this is to quantize model A that I wrote down before. The reason that you do this and don't put the theory on a lattice is that if you try to put the theory on a lattice, it changes the dipole and momentum algebra. And this is important, we believe. not to do, because when the dipole and momentum algebra is the continuum version, it's isomorphic to the Heisenberg algebra in one dimension. And indeed, as in textbook quantum mechanics, the Hilbert space actually doesn't have any singlet representation of this algebra. So there's a sort of tautological sense in which symmetry must be broken because you just can't find a wave function that's invariant under both momentum and dipole together. Okay. So in these two senses, I think it does look a lot like this theory must have spontaneous symmetry breaking. But there's a sort of awkward aspect of this symmetry breaking, which has been puzzling us for a while, which is that fluctuations of this field are very large. So just like the conventional Merman-Wagner theorem says that, well, the conventional Merman-Wagner theorem says you can't have SSB in 1 and 2 dimensions because the Goldstone boson's fluctuations are so large that they destroy long-range order. And we also have those long-range fluctuations here, as it turns out. And so this phi field sort of fluctuates strongly from one point in space to another. It doesn't have condensation in quite the same way as it would in higher D. But perhaps again, the non-compactness comes to the rescue because here phi is still a well-defined operator. So in a sort of tautological sense, even though it has large fluctuations, its average is still well-defined. And this is a little different from the compact Goldstone boson that we're more used to, where the physical operators are like e to the I phi. And those do always have a vanishing expectation value. So this is sort of maybe a cute way of seeing that there's an important difference between the compact and non-compact symmetry. Yeah.
So let's see. So in infinite volume, which I guess is the
So it's infinite volume, but finite particle number. That's the regularization that we're advocating for.
The infinite volume is crucial for this. The states that would be related by the dipole in infinite volume that you can worry about for particular dimension. I'll have to say they involve, you have to worry about boundary conditions that and those, it's normally not important, but here I think it's essentially because the states that would be related by symmetry, they obey different boundary conditions. That's maybe one way of thinking about why you can have the symmetry restoration in the dimension and yet have a Hilbert space with this enormous states related by symmetry. Once you project boundary conditions with a much smaller set of states. If you're in finite volume, of course, you don't have that choice. You have all of those states, you have to all of them. But of course, in that arena in finite volume, you really don't have symmetry breaking either. You just have states related to that.
Okay, so Kristen has a very extensive comment on boundary conditions at infinity. I won't try to repeat all of it, but okay.
I'm not sure that there's a contradiction here.
I mean, okay, in some sense, I also don't think there's necessarily any contradiction. I think what I'm emphasizing, I hope, is that it's just sort of unusual what's happening because sort of many, although not all of our usual metrics for symmetry breaking are obeyed. And I don't actually know of another example where sort of all of these ingredients come together in quite this way. That's all I want to point out. Okay, so that's really all I wanted to say. So just to kind of recap what I think is interesting about this whole story. So we're discussing essentially effective field theory for thermalizing systems, although they may not be at finite temperature. And these thermalizing systems have kind of funny multipole symmetries. There's also a story about hydrodynamics with subsystem symmetries. I would say there's a lot of sort of preliminary work on that subject. It could be a more subtle setting than the multipolar one, but there's some preliminary thoughts in the literature. I think personally the long-term vision for why these are important to study is probably not that the quadrupole conserving fluid is really important in nature. but rather that it's a stress test for our hydrodynamic field theories. And I think the existence of these models sort of forces us to think more carefully about the underpinnings of hydrodynamics as an EFT. And that is important. There are a lot of extensions, both in classical and quantum mechanics, where it will be important to have a better understanding of hydrodynamics as an EFT. In the shorter term, one nice outcome of this investigation has been a whole zoo of new dynamical universality classes that are sort of generalizations of the KPZ fixed point insofar as they arise out of the instabilities of constrained fluids at rest. So these aren't like turbulent instabilities where you have to push on the fluid, and if you push hard enough, the flow becomes unstable. These are like, you have a bunch of air molecules at rest, and yet there's no local PDEs that describe their long wavelength behavior. So it's a quite strong sense of instability. And then lastly, I talked about the notion of spontaneous symmetry breaking in fluids with momentum and dipole conservation. I think this is sort of it's a very curious field theory that I didn't get to really justify in this talk. But I hope that one sort of outcome of that will be a better understanding of coupling fractons to gravity. So with that, thank you.
I will take the mic for the questions.
John McGreevy raises his hand.
Should I go first?
Yeah, you can go first. Yeah.
Okay, thanks. So I wanted to ask, is there an understanding of the instability of the 1D ordinary Navier-Stokes stationary point to KPZ in this kind of Glorioso-Lou field theory, analogous to the one you described?
I'm not entirely sure, partly because I don't know how much of an answer you want. I mean, we can, I don't know that there's a controlled description of, like, we sort of know that in the Glorioso et al. Formalism, you can write down the equations and you know that they will indeed flow to KPZ, just because even without the field theory, that's sort of been established. But we don't have a local description of a field theory for that KPZ fixed point, and probably never can, because it has non-integer exponents. So,
but can you see the relevant operator that starts?
Oh yeah.
Starts you in that direction.
Yeah.
So the analogous understanding is the same to what you said.
Yeah. I mean, I think that the main thing, and from my view, about what's powerful about these field theory approaches is that, especially when you start talking about like KMS symmetry, this is very hard to impose at the level of equations of motion. And I think it's one of these things where after you see the answer, then you can post hoc justify everything. But if you want to get it right the first time, the action formalism is quite helpful. But for seeing this instability where KMS I don't think plays a crucial role, I don't know that it buys you much over the equations of motion.
Okay, thanks.
Any question in the audience?
So I had a question about the one-dimensional model you discussed before. In the Hamiltonian formalism you showed, the model is local, but the Lagrangian is non-local. I wonder if you had any comments on that and locality of these theories in general.
Yeah, so I would say we made that observation, and we didn't have much deep to say about it, so we didn't write it down. But indeed, these are systems where in the Hamiltonian picture, they're completely local. But yeah, just to repeat what was said, they don't have a local Lagrangian description. I guess my naive thought would just be that this just implies that there's the sense of locality as being that the microscopic particles have a Lagrangian is too strict. This is, yeah, I'm not sure if I have a deeper comment than that. these are perfectly sensible theories as we've written down. Okay, so I guess if you have so if you have a local Lagrangian and non-local Hamiltonian, I guess one issue is probably what degrees of freedom you're interested in. In the Hamiltonian picture, the degrees of freedom we care about are really the microscopic pi and xi. Basically, pi is the momentum, and the difference in xi's becomes the density in hydrodynamics. So if you, I guess the way I would interpret a system with a non-local Hamiltonian and local Lagrangian is sort of like the degrees of freedom where the theory is nice and local are not the natural ones. And so in that sense, it's not a useful description for at least the simulations that we're doing. But as I said, I don't know that I have a profound comment. It's a very interesting observation about these theories, right? That somehow only some descriptions of them are local.
Any question in the Zoom? Yes, John, go ahead.
So if you just do some like crude mean field theory, like Hubbard-Strauss-Novish kind of transformations on your field theory with this relevant perturbation added, can you get some guess about the nature of where it goes?
I would say we haven't tried in detail. I partly have a personal dislike of doing loop integrals if at all possible. So we haven't done them. But
Well, I was thinking of just saddle point analysis.
I see. I'm not sure that, I mean, things already look sensible. The action that we have is completely local for this theory. So,
but it has some nonlinear term, right? Some rho squared.
With the nonlinear term, yeah. But I'm not sure that it helps to do Hubbard-Strauss-Novish because so the nonlinear term will be something like a noise field times 2 copies of density. I guess you could try to say rho squared is its own field, but I don't know that it would really buy you all that much. But we haven't tried it, so maybe it does.
I guess since numerically you find z equals 4, there's a chance that it could flow to some simple local description, right?
I think that, but so in that case, the leading order piece is rho cubed. And there, I think it's just an accident of like when exponents. So if exponents are like 3.7, we can't really distinguish them from 4. So it could be flowing to a slightly different fixed point.
All right, I was being optimistic. Okay.
Yeah, but we've estimated it to be between 3.5 and 4.
Okay.
When you don't have the most relevant perturbation turned on. So.
All right, thanks.
Any more questions in the audience? No? In the Zoom? Okay, so maybe it's time to thank Andrew once more.